Recording. Hi everyone, welcome to Data Umbrellas webinar. I'm going to do a brief introduction and then I'm going to introduce our speaker who will do the talk, and then we'll have a question and answer session. If you have questions while the speaker is talking, just drop them in the chat or the question and answer tab, and then we'll read them out to our speaker and he'll answer the questions. This webinar will be recorded and it will be uploaded on YouTube in the next 24 to 48 hours. We are a community of underrepresented persons in machine learning, data science, and AI, and we are a nonprofit organization. Data Umbrella is run by a volunteer team. So here we have Reshma and I, and then we have 3 other volunteers who help make the events a success. We also have a conduct. We are dedicated to providing safe and welcoming, having a welcoming experience for everyone, and we thank you for helping make Data Umbrella a friendly community for all. How can you support us? So you can support us in various ways. One is by following our code of conduct so that we can help people come back, and since that will help them find Data Umbrella a welcoming and collaborative space. The other is sharing our events with others. For the ones who join our events every time, please share with your friends and colleagues so that they can also join our events which might be relevant to them. You can also contribute to Data Umbrella to open source. So one, we have a GitHub page where we have video timestamps. So for example, after this video is posted on YouTube, you can help us create event transcripts on our GitHub page. This will help this event reach as many people as possible. And then we are creating a new website. So if you have some experience in HTML, CSS, JavaScript, you can go onto our GitHub page. You'll find a repository for a new website. We also have a PyMC Sprint website, which you can help with that as well. We also have a Data Umbrella blog. So if you have experience working with Markdown, Jekyll, Git, and GitHub, that might be a good way to contribute to open source and Data Umbrella. And we also have an events board that we're creating that will help people get access to events happening in the data science field around the world. So if you have experience in React, JavaScript, Django, HTML, and CSS, you can help us. Also, people who do design work, UI, UX, that would be a great way of contributing to open source. You can also donate to us on Open Collective. We're on Open Collective as Data Umbrella. We're also on Benevity, which is a company matched platform. You can subscribe to our YouTube channel. In our YouTube channel, you'll find different libraries like career advice, data visualization, contributing to open source, scikit-learn, PyMC, and NumPy. You can also sign up to our monthly newsletter. We release newsletters once a month at the beginning of the month, and we promise not to spam you. So our newsletter is on Substack. You can join Substack and on our website, dataumbrella.org. On the resources, you can find lists of conferences, open source resources, accessibility and responsibility, AI ethics, and more. We are also on all social media platforms. So you can find us on Twitter, LinkedIn, Facebook, and Instagram. You can go through our website. You can follow us on Meetup, where we post all our events. We have a YouTube channel where we have posted so many of the events we've had. We have our newsletter. GitHub is where you can find ways in which you can contribute to Data Umbrella and open source wide. And then we also have a job board. So for those looking for jobs in the field of data science, jobs are posted there regularly, and our jobs are jobs.dataumbrella.org, or you can go to our website and look for that tab as well. We also have live captioning for this event. So if you want to use a live captioning while this event is continuing, look on your right, I suppose, you'll see a CC button where you can use that in case you need that during the event. So we have an online suggestion box. So this online suggestion box is shared on the handout. So it's a form where you can give us suggestions for future event topics, feedback on this event, technical issues in case of any, and any other general feedback that you think might be helpful as we grow Data Umbrella as a community. We have 3 upcoming events. We have an event on June 27th, which is on Vicuna. Vicuna is a chat box open source tool, which encompasses GPT and LLMs, which are large language models. So if you're interested in that, you can tune in on that event on June 27th. We have a July 11th event on Quarto, and we have a 25th July event on machine learning visualization using Yellow Brick. Where you can find all these events and links to sign up to them is on Meetup. You can join Meetup, the Daruwalla Meetup or the Daruwalla Africa Meetup page. On today's talk, so today's talk is Intro to Flux and Machine Learning in Julia, and our speaker is Kyle. So a little bit about our speaker today. So Kyle is a neuro AI scholar at Cold Spring Harbor Lab, where he conducts research at the intersection of computing, machine learning, and neuroscience. He received his PhD in electrical engineering from the University of Wisconsin and Madison, studying von Neumann computing. He can tell us what that is. He's also currently a commentator for the FluxML organization. You can find his social media links, which are GitHub, LinkedIn, and Twitter, on the slides, which have been posted on the handout section in case you need to connect with him. And with that, I will now let Kyle take over and begin the talk. Welcome, Kyle.
Great. Thanks for the introduction, Beryl. Let me share my screen. All right. Hopefully everyone sees my first slide. Hi, happy to be here, and thank you for the invitation. So today I wanted to basically give a high-level introduction to FluxML, which is kind of the foremost machine learning package in the Julia programming language. And so today's talk is really geared at beginners. I assume you might have some background in machine learning. Maybe you've played with some machine learning frameworks in Python, for example. But I'm assuming that no one here has had an introduction to Flux or to Julia, but I guess it turns out that a bunch of you have tried Julia before. Yeah, for the rest of the talk, I'm just going to give like a high-level overview of some basic tutorials in Flux and Julia, just to give you a flavor of what machine learning looks like in Flux and where to look for further resources so that you can learn more. Okay, so before we can get into Flux, I wanted to talk about Julia itself and how it's different from maybe some languages that you're used to. So Julia is a dynamic programming language. So what that means is that you can expect a familiar syntax to MATLAB or Python. It's a high-level language, and it has the kind of interactivity that you expect with something like Python, which is really important for data science, where you need to be able to iterate and rapidly develop your code. But a unique feature of Julia in comparison to those other languages is that it has ahead of time compilation. So what this means is that when you call a function in Julia, it runs, you can call it interactively in a REPL like you would in Python, but the Julia compiler will actually statically compile this function the very first time you call it. The very first time you run your program, maybe you pay a bit of penalty for compiling that program for the first time, but then subsequent times you try to call that same function, it's already been compiled, and so it should run as fast as a statically compiled language like C. And that's exactly the kind of situation that we want in machine learning, where we have interactivity, but you also have speed. And another kind of important point is that Julia was designed from the very beginning for scientific computing. And this is a much larger field in machine learning, but the kinds of constraints that scientific computing places on a programming language are similar to the kinds of constraints that we would want from a programming language suited for machine learning. So examples of this is arrays and linear algebra being taken seriously and being built into the standard libraries of the language itself, instead of people needing to develop specialized array-based packages on top of a host language that doesn't have any native support for multi-dimensional arrays or linear algebra. And so why choose Julia for machine learning over some other language? I think the first point, which matters to me a lot in my everyday, but I think really gets lost a lot of times when this is brought up in online forums, is that Julia has a very sensible and well-designed package manager. When I work on projects in my day-to-day work that don't involve Julia and use some other framework based in Python, I can measure in time the amount of hours I've lost to my environment getting messed up somehow by Anaconda, and or my libraries, CUDA libraries, getting out of sync with Python packages that are installed. And so the Julia package manager has been designed really to try to address some of these issues. So for the example of CUDA, which is essential for any machine learning library, those binaries are built specifically for the systems that you can run Julia on, and they're versioned and shipped by the package manager. So instead of having to install CUDA yourself and make sure it's in sync with a package that's been installed by Julia, instead you just install the Julia packages, and alongside with that come all the other external libraries that you'll need, specifically selected for the hardware that you're trying to run on and for the version of CUDA that you're trying to run with. Another important point is that the way the package manager is designed, you'll see a lot of Julia programmers create different environments for every project that they work on. And what this really encourages is to have reproducible work, which is an important consideration when you're working in data science or machine learning. Then going away from the package manager to features of the language itself, Julia has a feature called multiple dispatch, which I'm going to explain more in detail in the future slides. But really, this combination of multiple dispatch and the array interface introduced in the base Julia programming language allows us to write machine learning code that specializes for different hardware devices. And this is really important so that you're getting the maximum performance that you possibly can on the hardware that's available to you. And then this last point is, I guess, something that we won't go into in much detail today, but it's what actually drew me to Flux and Julia in the first place, is that Julia has support for meta programming and code reflection. And so what this means is that you can write Julia code that takes in as input another Julia program or function, and it has a representation of that program and function in Julia itself. And then you can manipulate that representation for example, optimizations on it, and then generate new Julia code after those optimizations have been done, and then run that code that you've generated. And this is really important for the automatic differentiation engine that's the default in Flux. It's a source-to-source automatic differentiation engine, which means that it takes in an arbitrary Julia program and then transforms it to produce a new program that does the backward pass, that does the differentiation that's so essential behind any machine learning package. And then, of course, lastly, Julia is a language that encourages REPL-based development, and we're really going to see that in today's talk. And I think this is crucial for any data science application. You want to be able to develop a script that you could run a long-running job on, but at the same time be able to run portions of that script interactively so that you can effectively debug and iterate on what you're working on. And the tooling around the REPL and the Julia extension in Visual Studio Code really makes this, I think, much easier than you'll find in other languages where you're pushed more into having a script versus having, let's say, a Jupyter notebook. All right, so now before we go into Flux, let's just do some beginner exercises with Julia itself, just so you can get a flavor for some of the features I just talked about. So like I mentioned, we're going to do everything today in the REPL. And so if you download the Julia binary and you run it, you'll get the REPL as your prompt. And if you're following along with the video, I'm going to introduce some packages along the way, and you'll need to install those packages. And to do that, you need to enter the package mode of the REPL, which you can do by hitting the right square bracket key. And if at any point you're confused about what's going on, you can press the question mark key at the REPL, and that will bring up the help prompt where you can type in the name of any function that you don't understand or want to know more about, and it'll give you documentation and links for where to go to understand more. And I'm not going to go into all the details about the REPL today, but if you want to learn about what I just said and additional features that it has, you can visit the link at the bottom of this slide to read the documentation on the REPL. So the first step in any machine learning framework is to create your first array or tensor. And so this is how you would do that in Julia. So here I'm creating a 2D array of all ones. So if you're coming from NumPy or PyTorch, you might be familiar with the ones function, which lets you give a shape and it'll create an array of all ones given the shape that you give it. And so here I created a 2x3 matrix of all ones. And so we can see the shape of the matrix here in the REPL, and then we also see its type. So we see that the elements of this matrix are 64-bit floating point numbers, but we could specify another type to the ones function to change the element type that it creates. You can also create, in this example, a 3D vector or 3-element vector of ones as well. And in this case, I'm scaling up all the elements by 2, and so I get my vector with all 2s. And so one thing I want to highlight here is the fact that in the first case, you got a matrix. In the second case, you got a vector. So if we look at the number of dimensions of each of these 2 variables that I just assigned, you can see in the first case, it's 2D. The second case, it's 1D. So by default, vectors in Julia are column vectors. And this is something, because Julia is specifically designed for scientific computing, that the designers of the language have taken very seriously how multidimensional arrays work. And just as a small note, if we look at the type of each of our variables, x and y, we can see that in the case of the matrix, this is really just an alias for the underlying array type in Julia. So there's an array type in the base language itself that has support for arrays of different kinds of elements, and then also directly supports multi-dimensional arrays. So you don't have this kind of situation where you have lists of lists like you might in some other languages. And then so same thing with our vector, we see it's a 1-dimensional array. And so the reason that I say that the Julia designers have really taken into account how multi-dimensional array should work at the language level itself, is we can do something like multiply x by y, and normally you would need maybe a special operator like matmul or the @ symbol if you're coming from NumPy to do a matrix multiplication. But here, due to the combination of the specific types assigned to each array, as well as multiple dispatch, Julia knows that you're multiplying a matrix by a vector, and so it executes a matrix multiplication instead of trying to multiply these 2 things element by element. And then also, Julia specifically separates the notion of a column vector from a row vector. So if I take the transpose of my vector y, we can see that it's now actually a 1x3 array that's a row vector. And so what this means is that all those operations that you might see in theory that are written using linear algebraic notation can almost directly be translated into Julia code, and it just works. So I mentioned here that if you try to multiply x by y, you end up doing a matrix multiplication. But what if you wanted to multiply things element-wise? Well, there's a feature built into Julia called broadcasting that allows you to do that, where you can add a dot to any function, and now we'll try to broadcast that operation across the arguments. And so this might be familiar to you if you're coming from MATLAB, where you can also do element-wise operations there by using a dot. And if those two operations are the same size, it just does it element-wise. But one kind of nice feature of how it's implemented in Julia is that you don't need to have elements of the same size. So here, X is a 2x3 matrix, as we can see in the top left, and Y is a column vector that we transpose. So it's 1x3 row vector. And so I have 2x3 multiplied by 1x3, and I still get a valid operation, because what Julia is doing is it's broadcasting that row vector across the rows of my matrix. And so this is similar to broadcasting operations if you're familiar with NumPy, except for in Julia here, it's a little bit more the name f. And so I can have one function, one symbol f that refers to this function, but I can have many methods or implementations of that function in the language. And so here I just have a single implementation, the one I just defined. And you can see if I call f on the number 2, I get the output I expect 4. Where multiple dispatch comes in is now I can start adding type parameters to the arguments of the function. So here I again defined f, but now I specified that this f only applies when the input is an integer type. And in that case, I'm going to do something completely different. I'm going to take the square root of the input. And so now you can again see I have my same function f, but 2 methods associated with it. And so if I call f on an integer, now you can see I get the square root of 2 instead of getting 2 times 2. But if I call it on a floating point number, I get the output 4, which is what the original function did. And so if I look at all the methods associated with f, you can see I have 2 options. I have one f for integers and then another one for any type. And so what multiple dispatch means is when I call this function, it's going to look at the type of the arguments, and it's going to try to match the method where the type signature most closely matches the types of the arguments, and then call that specific method. And so where this can come in really handy for machine learning is to write highly optimized code. So one thing you may be familiar with, and if you have any ML background, is the concept of a one-hot array. So this is usually used, for example, for classes when you're doing image classification, where you have a vector and only a single element of that vector is a 1, indicating the class that input belongs to. And so here I have a set of classes from 0 through 5. So this colon notation in Julia, it should be familiar to anyone coming from MATLAB, but if you're coming from Python, this is similar to a range. So this is basically saying, give me a list from 0 through 5, just like you would with range. And so I'm going to sample from that set of labels. I'm going to select 4 random labels from this set, and those are going to be the indices that my different inputs belong to. And so here you can see I got a vector of 4 indices that were randomly selected. And there's this one hot arrays package that we maintain as part of Flux that can translate that vector of indices into the one hot representation that we use typically in machine learning. And so now you can see I have this 6x4 one hot matrix. Why 6x4? Well, you have 6 rows because we have 6 labels 0, 1, 2, 3, 5 in our original set that we sampled from, and then 4 columns because we sampled 4 different indices. And you can see each column has a single 1 in only one place. And the important thing to pay attention to here is that the underlying storage is just this vector of indices. So this 6x4 matrix would otherwise take up 24 elements, but we're actually storing it in this compressed representation. And that's really one of the key advantages of having this special one hot array type. Another advantage is that when you try to multiply some matrix with a one hot vector, that's equivalent to indexing the columns of that matrix. And this is important in specific types of machine learning layers, such as an embedding layer. And so here I made up some random embedding by just generating a random 3x6 matrix. And so the 3 is my embedding dimension. And then the 6 is what's called like the vocabulary of the matrix. So I have 6 possible words in my vocabulary to choose from, and each word is represented by a 3-dimensional vector. And so now I want to select some words from this embedding matrix, and I can do that by multiplying it by a one hot vector. And if I just use a traditional standard multiplication function, then this would end up incurring extra compute when I have to do this matrix multiply, extra memory allocated to do that matrix multiplication. But in Julia, I know that the type of this operand on the right is a one hot array. And so I know that this is really just an indexing operation. I don't actually need to do a multiplication. And so that's actually exactly what happens here in the one hot arrays package. And the reason it's happening is because of this special combination of multiple dispatch and specialized array types. And so if I look at which method is actually getting called when I do this operation, I can do that in the Julia REPL by using this macro called @which and then passing it the operation, and then it'll tell me which method gets called. And so here you can see that it's calling a method in the one hot arrays package that specializes on the second operand of the multiplication as being a one hot array. And so this is how we can have specialized versions of certain operations that are tailored to either the type of the operands being resulting in faster operations, or maybe the type can actually encode something about the hardware that this operand is stored on. And so that's what we're going to look at next. So here I'm using the CUDA library, which is a package in Julia that allows GPU programming on NVIDIA GPUs. And so I've generated a random 3x4 matrix of numbers, and this is on my CPU. You can see that it has a standard matrix type. And now I'm going to call this coup function on that same variable x, and now I get a new variable y that has a type coup array. And so where this can be used to our advantage is we can have specialized operations that run on CPU arrays versus GPU arrays. So here again, I define some function f that just multiplies its input by 2 like before. And then I have a specialized version of f that operates on any array of any type as long as it adheres to that array interface. And in that case, I call the square root on the input. And then I've also defined a third method for f, but here I specialize the type as QArray, and in that case, I square the input. So you can see if I call f on a single number, I get 2 times 4, which is 8. But if I call f on my CPU array x, then I get the element-wise square root of the array. And if I call it on my Q array, my GPU array y, I get the element-wise square. And then all of this is actually computed on the GPU because that's the host device that is storing this particular piece of memory. And so this is a feature that we really leverage a lot in Flux in order to make sure that models and data that are stored on the GPU actually dispatch to fast optimized versions of various operations like convolution or matrix multiplied that run as fast as possible on the hardware device that we care about. Okay, so that's a brief introduction to Julia. Now I just want to give you an overview of the FluxML ecosystem and then quickly go through some examples of training a model in Flux. And so the FluxML org is an umbrella organization that has a lot of different packages that we maintain all around machine learning and specifically around Flux.jl, which is the neural network package in Julia. And so if you go to fluxml.ai, this website right here, you'll find kind of the entry point to our org, our documentation, examples of various models written in Flux, as well as links to other packages in the ecosystem. And so one of the overwhelming things for a lot of people in Flux and Julia compared to something like PyTorch is how distributed all the code is. In PyTorch or other frameworks, a lot of the code is developed in like these monolithic repos, whereas in Flux, we try to decompose and separate out all the pieces as much as possible. So Flux is actually itself a very thin layer that just defines some neural network layers on top of a whole bunch of other packages that actually do the heavy lifting. So Zygote is our automatic differentiation engine. So it's a source-to-source AD system that allows you to differentiate arbitrary Julia code with a few exceptions. This is very different from, let's say, automatic differentiation in other ML frameworks where the only things you can differentiate are the operations that are supported and defined within the framework itself. NNlib is a package that hosts those specialized implementations of various operations like convolution or pooling. Optimizers.jl is the package that defines all the optimizers that we use, such as Atom or gradient descent. And then functors, this is a bit of an advanced package, but this is really a package that allows us to manipulate not just the layers that we define in Flux.jl, but custom user layers in a way that's kind of transparent to the user. So there's custom user layers are like first class layers in Flux. And then so on top of all of those, Flux defines some default layers like fully connected layers, convolution, residual connections, and then there's a whole suite of packages based on top of that extend those layers. So for example, transformers.jl gives you transformers like GPT built in Flux. Metalhead.jl gives you computer vision models like ResNet built in Flux. AlphaZero is an implementation of DeepMind. DeepMind's AlphaZero reinforcement learning model in Flux. And then we also have graph neural networks for graph neural networks and Flux training, which you can think of as similar to PyTorch Lightning. So Flux.jl itself doesn't provide a lot of training utilities. And so to get things like logging and learning rate scheduling and these data augmentation, these kinds of things working, you would rely on a package like fluxtraining.jl, which is kind of the underlying training loop package that fastai.jl is built on. And fastai.jl is kind of a Julia version of the very popular Python fastai package. And so FastAI brings together everything here that I talked about with Flux through FluxTraining.jl in combination with some data wrangling utilities provided in ML utils, data sets provided by ML datasets, augmentation provided by data augmentation, learning rate scheduling provided by parameter schedulers.jl. And you should go to this ecosystem link if you want to find out more about these specific packages and how to get started with them. And I won't go into too much detail on most of these packages today. So with that, let's go through a simple linear regression model in Flux. So this is kind of a hello world for machine learning. And so here is our ground truth model. We have some inputs X. We're going to multiply it by a weight W, add some shift or bias B, and that gives us our output Y. And so this is a simple linear model. And in this case, the ground truth, we're going to choose a very specific W and B that gives us a very specific linear function or line that we want to fit. And so this is how we would define that in Flux. Here I define a function called true model that takes an input X. And then here I've chosen W to be 4 and B to be 2. And I just do 4 times X plus 2. And that's how my function's defined. And so now that I have this true model, I can use it to generate data. And so here I'm going to generate some examples of the input X for training and then for testing. And so my training data set is just going to be 0, 1, 2, 3, 4, 5 as my values for X. And my testing data set is going to be 6, 7, 8, 9, 10. And now I can evaluate my true model on both the training data and on the testing data. And here you see, again, I'm using that broadcasting operation with a dot to evaluate this model in one step on all the different elements that compromise my make up my training data. And so here I get my outputs, Y for the training and test data set. And so here we can use one of my favorite packages, Unicode plots, which allows you to do plotting right in the REPL to visualize what the training data looks like. And so on the x-axis here is the input X, and on the y-axis is the output Y of my linear model. And then each of these points are the points in my training data. So now that I have a ground truth model defined, some data generated from it, I need to now fit a new model to the ground truth. And so I'm going to define a new function that I'm just going to call model. And unlike the previous function here, W and B are inputs. So W and B are unknown, and these are the two things that we're going to want to learn and fit to our data. And you can see the model is the same as before. It's just a linear model. And since we don't know what W and B actually should be, we're going to select 2 random values as our initial conditions for W and for B. So here I just randomly sample them from a uniform distribution, and you can see that both W and B are nowhere close to the true values of 4 and 2. And so we can again use Unicode plots to visualize how this initial model performs on our data set. And so I'm evaluating our model with the initial W and B on the training data, and then I'm plotting that. These green circles are the original true data set, and then these blue X's are the predictions from our model on the X inputs. And you can see it's pretty far off from the actual line, and that makes sense because we haven't learned anything yet. So in order to learn something, we're going to run a gradient descent algorithm. And in order to do that, we have to be able to take a gradient. And so here's how you would do that in Flux. We're going to call a function called flux.gradient. And then we're going to pass it our initial values of W and B, which are the points around which we want to take our derivative. And of course, we need something to take the derivative of. And so to do that, you would normally pass a function that defines the thing you're trying to take the derivative of. And we can do that using this do syntax, which is a special syntax in Julia that defines an anonymous function. So if you're coming from Python, this is similar to a lambda expression, except for the do syntax allows you to really conveniently write a multi-line anonymous function and pass that multi-line anonymous function in as the first argument to this function gradient. So let's look at what that function looks like. Here, the anonymous function takes two inputs, W and B, and then it calls our model, passing in W and B, as well as the full training data set. And now our model produces some prediction Y, and then we calculate the mean squared error between our predicted Y and the actual true training Y. And so Flux will take the gradient of this function that we've defined and now spit out a derivative with respect to W and a derivative with respect to B. And so that's what we see here as the output of this gradient call. And so now that we have derivatives, we actually need to update the parameters of our original model. So we're going to do that with gradient descent. Here's just a very manually written implementation of gradient descent. So I take my original W and I follow the, I update it by following a tiny step in the direction of my gradient dW. And so you can see that now my W has been updated and it's a little bit closer to the true value of 4 from my original value, which was around 0.9. And the same thing can be done for B. And then we can again plot the performance of our model right now. And you can see in green, the original, the true data set. In blue X's, you can see the original model. And then in red diamonds, you can see our new model. And so the line has moved a little bit closer to the true line. And so we're a little bit closer to our optimal value. And so here we kind of did everything manually. We were manually keeping track of W and B, manually passing it into our model and updating them. And of course, if you try to scale this up to a neural network, it's just not going to be feasible. And so that's where Flux actually comes into play. It allows you, it gives you a set of default layers, as well as the mechanism to define layers of your own. And so here's an example of me defining our linear model as a layer in Flux. So I'm going to define a struct. And so this is the Julia equivalent of a class in Python. And so a struct has some type, a name, just like you would for a class. And then it has fields that are the data that are contained within that struct. So here I have two fields, one for W, one for B. And then I'm going to call flux.functor on my new type that I just defined for my layer. And this step is important so that Flux knows how to take apart this layer, update the parameters, and put the layer back together into the type that we defined. And then once I have this layer, you actually need a forward pass for the layer, a definition for what the layer actually does to an input. And so to do that, I can define a function just like I did before, except for here, the name of my function is now actually this, is an instance of this linear object that I just defined. And so M is going to be a particular instance of a linear object. And then I can access the fields of M as part of the definition of this function. And so this is how I define a forward pass for my linear layer. I define it as each instance being callable on an input. And I do the same thing as I did before. I multiply by W and I add my bias B. And so this is the syntax for how you would define a forward pass in Flux. This is familiar. If you're coming from Python, this might be similar to the call, a special call function that you can define within a class to make a class callable. We're doing the exact same thing here and making this struct callable. And so once I have my struct, now I can initialize a particular instance of it, passing it, in this case, the current values of W and B that I have. So here I have a particular instance that I've assigned to a variable linear model. And so now again, I can take the gradient as I did before. but instead of manually passing in the individual parameters of my model, I just pass in the model as a whole. And my anonymous function, instead of getting the individual parameters as arguments, gets the whole model as an argument. And I call that model on my input training data. I again produce predictions and compute the mean squared errors as before. But now when I take this gradient, I get a single derivative back for the entire model. And you can see that this derivative has kind of the same structure as the linear model. It's not going to be the same type as a linear model. In this case, it's a tuple, a named tuple, but you can see it has the same fields, W and B, and then the gradient associated with those fields. Okay, so I have one last thing that I want to go over, which is going through a more complex example, training an image classifier in MNIST, but I'm going to briefly pause just to see if there's questions before we do that. And I can't see the chat, so in case there are questions, maybe someone can read them out.
There's a question there. What books/courses/
anyone, if you have a question?
Sorry, there's a little bit of an overlap.
Go on, Reshma.
Go ahead, Beryl. There's a couple of questions in the Q&A.
Okay, so there's a question. What books, courses, or communities would you recommend for those wanting to get into machine learning with Julia?
Into machine learning, or specifically machine learning in Julia?
Machine learning with Julia.
So I think for a general introduction to Julia, I would recommend the book Intro to Julia by Tom Kwong. And then for machine learning in Julia specifically, I think there's a book about to be released. I'm not sure if it's actually been published yet, but there are plenty of tutorials available online on our own website and on other places, and I have linked to that at the end of the talk.
Okay, then there's a question. Are there any GitHub repos you would recommend for Julia-based machine learning projects?
Examples of machine learning projects in Julia. Yeah, there's I guess I would recommend looking at our model zoo, which basically has projects organized by topic, such as reinforcement learning, computer vision, text generation. And then you can go in there and there's a self-contained project that implements whatever the task is using Flux and Julia. That's what my recommendation would be for best practices. And the link to the model zoo is right at the top of our website.
Yeah, you can go in the presentation, and then we can have the other questions after that.
Okay. All right, so this is the last thing I'll go through and then conclude. And so here is giving you more of a flavor of what typically machine learning will look like in Julia, because most of us won't be doing a linear regression task. So here we're going to load the MNIST dataset. And so I mentioned that library initially, ML datasets. And so we're going to use that here to load MNIST. So we can see here we have our training data. If you're familiar with MNIST, it's 28 by 28 grayscale images, 60,000 of them in the training set. And so that's what our features are. And then our targets are indices, labels associated with each feature between the digits 0 through 9. And again, we have 60,000 element vector of integers. And then we can also choose to have this test set, which is another 10,000 of the same kinds of examples. And so once you have the data set, we're not going to evaluate our model on the full data set all at once. We're going to evaluate it on batches of data. And so we need a data loader in order to load the data in batch by batch. And so that's what I'm showing here. I'm writing a quick utility function that'll take in some data set, an MNIST data set, and then spit out a data loader that's ready to be iterated batch by batch. And so here it takes an input, the data set, and then also a keyword, the batch size. And first thing it does is it reshapes those features, those 28 by 28 images, into flat vectors. And then it also encodes the targets, the indices, as a one-hot matrix. And so once I have those two pre-processing functions done, Flux has a data loader built in that you can call, that you can pass that data to, also give it the batch size. In this case, we want to reshuffle every time we iterate through the data set. So the data loader will take care of all of that for you, and it'll do the data loading in the background in parallel while you're running your training. And so here I use my utility function to define a data loader for my training data. So you can see that it has a batch size of 64. And that it also prints out the shape of the first element. So you can verify that, yes, now I've flattened my inputs into a flat vector, and then I've also one-hot encoded my targets. So once you have a data loader, you also need a model and a loss in order to train something on that data. And so here's how you would define a multi-layer perceptron in Flux. So dense is a fully connected layer. So our input is 28 times 28, 784 dimensional vectors. I'm going to map it to some hidden dimension of size 64. I'm going to use a ReLU activation function, and then I'm going to subsequently pass it into another dense layer that then maps it down to the 10 classes that make up our output. And I'm using this chain. It's similar to sequential from PyTorch. Or JAX if you're familiar with that, but it basically lets you run a sequence of layers one after the other. And so here I'm going to define my loss function. It takes in my model, a batch X and a target batch Y, and then evaluates my model on that input. That gives me my predictions. And then I'm going to use the logic cross entropy loss between those predictions and the true targets Y, and that's going to be the loss function that I return. So here, for example, I can evaluate this loss on the very first batch in my train loader, and the loss is about 2.2, which we'll see how to drive that down in the next slide. Also, in addition to the loss, you want to have some way of measuring the performance that you actually care about, which in this case is our ability to classify images correctly. So here I'm going to define an accuracy function similar to the loss. It takes in the model and then the X and Y that make up my batch. And flux.oneCold is kind of the opposite of a one-hot operation. So it's going to take the output of my model. It's going to translate it backwards from one-hot vectors to indices, indicating which class the predictions belong to. And I'm going to do the same thing for my one-hot labels Y, and then I'm just going to see, is the class that I predicted equal to the class that I need, and then take the average of the number of samples that I got correct in the batch. And so here's another example of multiple dispatch. I'm defining accuracy again, but instead of passing it 3 arguments, I'm only passing it 2 arguments. The second argument is going to be a data loader, and so now I can define an accuracy over a full data set split by iterating each batch in the data set, evaluating my other batch individual accuracy function on that batch, and then taking the average across the full data set. And so here, for example, I build my test loader and I run my accuracy function on the test loader, and we can see our accuracy is about 7% to start off. So once I have that, I have all the pieces to write my training loop. So I'm going to choose the atom optimizer to optimize my model, and this is how you would instantiate it in Flux. And then I'm going to write 2 for loops to iterate over my data set. I'm going to have a for loop over epochs, 30 epochs in this case, which is how many times I go through the full data set. I'm going to have some temporary variable to track my loss over the full data set. And then I'm going to have another for loop, this time iterating over batches in my training data. Then I'm going to call flux.withGradient. This is similar to the gradient function before that we saw, except for in addition to returning the gradient, it also returns the value of the loss at this particular batch. And so here before we were using the do syntax because we had to write a multi-line anonymous function. Here's a inline anonymous function, not using the do syntax. And so you can see we pass it as the first argument to our gradient function. Oops. And then also pass in the model, which is the point around which we want to take the gradient. So now I have my loss on my batch and my gradient. And I can call flux.update, passing it my optimizer, my current parameters, and my gradients, and I'll get back the updated state of my optimizer, as well as an updated version of my model. So I do that in a loop for the full training data set, and then at the end of that, I print out what is the average loss, as well as the average test accuracy on this epoch of training. And then that's all there is to a simple training loop in Flux. And so if I hit run, you'll see this print out, run epoch by epoch and print out your average loss, which you can see is going down. And then the accuracy, even within a single epoch, jumps up to 93% and then keeps going from there. All right, so that's basically the end. Last thing I want to leave you with is some links for where to go for next steps. First, of course, is our documentation. If you go to fluxml.ai, there's a link to the documentation at the top of the page. You'll find, for example, this fitting a line tutorial, which is one of the tutorials I just went over today, as well as a whole suite of other tutorials to help you get started, and as well as links to the ecosystem and other packages to look at. I also wanted to encourage anyone who's interested to just dive in with the jump in feet first and become a contributor. This is how I got involved in Flux as well. In comparison to a lot of machine learning frameworks, Julia is very easy to read the source code. There's not that many lines of source code to take in to understand how Flux works. And I encourage every one of you to just go directly to the Flux.jl repo and try reading the code and see if you understand it. With a little bit of beginner Julia knowledge, it should be easy to understand, and you should be able to see even low-level details like how we call specific CUDA functions for things like convolution, for example. And then in terms of resources to connect with us, Julia has a discourse forum, and there's a specific machine learning tag in our discourse forum. Flux itself is maintained by a community team of maintainers, so you can follow this link to learn more about that team, and as well as join us if you want to. We also have a Zulip stream where we coordinate our development, and so here's the link to that Zulip stream. There's also an official Julia Slack, which you can join, and it has a Flux and machine learning channel to connect with us. Here's a link to that Zulip server I just mentioned. And then the last thing also is that we have bi-weekly calls for machine learning in Julia that happen every 2 weeks. And those are typically recorded and posted on YouTube. So you can join the bi-weekly call Zoom link and actually participate, ask us questions, bring up concerns, as well as if you miss the call or you can't make it, you can go to this link, which will take you to the YouTube channel where you can actually listen into those calls after the fact. And then the last thing, JuliaCon is coming up at the end of July. Tickets are now available, so you can go to juliacon.org to get a ticket for this year's upcoming JuliaCon, where you can connect with devs not just for Flux, but for other big ecosystems in the Julia language. So with that, I'll stop and take any questions. Thank you, everyone.
Thank you, Kyle. I have a question. So JuliaCon is both online and in person, or is it in person only?
I think it's primarily in person. I'm not sure if I think the talks are live, but I know they will be recorded.
Okay, thank you. We have a question, which is, does the advantage of Julia only apply to machine learning?
No, so I think machine learning is one of those cases where at least the main advantage of Julia, which is the performance, is actually hard to beat some of the existing frameworks, because a lot of things like PyTorch actually end up calling into C libraries. So a lot of engineering effort has already been spent to make sure PyTorch and these other frameworks are as fast as they can possibly be. So machine learning, to see an advantage in Julia, you really need to be working on maybe some esoteric or kind of bleeding edge cases. And so actually where I think you see most of the performance benefits of Julia are in cases like scientific machine learning, where it's not a traditional use case, and the scientific machine learning community is fairly big in Julia. And they'll actually have like a separate conference just for scientific machine learning co-located at JuliaCon. So yeah, I think it extends to more than just machine learning, more scientific computing in general.
Great, thank you. We'll wait a couple of minutes just in case other people have questions. Yeah, so are you presenting at JuliaCon this year?
I'm not presenting, and this year I actually won't be at JuliaCon because I have some conflicts, but there should be other devs there from Flux, I think.
Okay. We have another question, which is, what areas of machine learning are Julia/FluxML mainly useful? For instance, for regression, NLP, image classification, etc.
So there are examples of all of those in Flux. I think the one that their existing tooling has the most support for right now would be Envision, but we're building up the language aspect. And then in terms of linear regression, that's fairly easy to do already in Flux, but if you're in that kind of situation, you may also be interested in more classical machine learning techniques. And so there's an entire set of packages for those kinds of techniques in machine learning that are pretty mature at this point in Julia. And those would be useful, yeah, for cases like regression.
Next question is, can you describe the difference in your function between parameter _m versus m?
Oh, yeah. So I think you're talking about on this slide. And so the only reason I put an underscore here is to really make explicit that this m is a different variable from this m. So this m is the particular instance of my model that I'm training, whereas here I'm defining a function that takes one argument. And so, you know, when you call a function in Julia and you pass it some input, those arguments are bound to variables. And so I'm trying to make really explicit here that this refers to the input to this anonymous function. I could have called it m, but then it would have just been a little bit confusing from like a coding design perspective.
Got it. Thank you. And so one last question, which is there anything that we should know about Julia related to ChatGPT, or like uses, like if you've seen useful use cases or just any connection to it that we should know about?
I believe there is a package out there already for calling ChatGPT from within Julia. And I think it's called ChatGPT.jl, but don't quote me on that. But if you search ChatGPT Julia package, it should come up. But yeah, I mean, we have that, and then we also have alongside that the transformers.jl package, which is if you're more interested in training these models and actually working with them, then I would look towards that package. But I don't know that we have pre-trained weights, let's say for Llama existing in Julia yet, but hopefully soon.
Great, thank you. So with that, we're going to end the webinar. Thank you so much, Kyle, for presenting. I know I think we started our email thread quite a while back, so we're very happy, that you were able to share your expertise with the community. And thank you, everybody, for joining us. And the video will be available within 24 hours. Thank you.
All right, thanks, everyone.